Okay, look, I hope you've had a chance to think about what we've been going through here. Just as a quick summary, all right, this of course is our state diagram, which is basically describing the operation of that traffic light system, what we want the traffic light system to do. Here we have the state table. Really, the state table was developed by considering this state diagram. S, A, and B are inputs. A and B, of course, represent the present state, the state that we're currently in. S, of course, is the switch. And then, of course, we have these as outputs. AN and BN are special outputs. They are next state outputs. And then, of course, we have our lights over here. Okay? The state table is really just describing basically the relationship between these outputs and these inputs over here. So in essence, that state table is a truth table that will allow us basically to design the logic that goes in this block over here. And that's what we did last time, if you remember. And so really to actually come up with the Boolean equations, we took each one of these outputs. For example, we would take AN, we would come down the column for AN, identify the first product term, read across the input combination that's required to produce that product term. And in this case, for example, this would have been what? Don't care about the switch, but we do have A bar B. So the first product term is A bar B. Continue on down the column, next product term. Don't care about the switch, but we do have A, B bar. And so very quickly then we could write down the Boolean equation then for AN. And we did the same sort of thing for BN and then all of our light conditions over here. And we ended up with a set of Boolean equations. Now it is from that set of Boolean equations that we can actually draw or design the logic. Okay, so here is that set of Boolean equations which has been summarized. So we've got equations for AN, BN, all of our light conditions. And now what we'll do is we'll go ahead and draw the logic to actually implement those Boolean equations. Now what I thought I would do to start with though is I thought I would actually define, if you like, by way of a piece of wire, okay, maybe what I'll do here is I'll draw a line coming down like this. And I'll say this is a wire that corresponds, let's say, to A. And then maybe I have another piece of wire right next to it, and I'll say that this is the piece of wire that would be for, let's say, example, A bar. And then I'll do the same sort of thing over here. A piece of wire, this piece of wire will be the piece of wire for B, and then we'll have another piece of wire sitting over here. This piece of wire, of course, would be the B bar, as it were, piece of wire. Okay? All right, so let's look at maybe first of all north-south green, implementing that. What do we have? We have effectively an AND gate. So let me go ahead and put this in the north-south green condition here. So I'm going to take an AND gate, a 2-input AND gate. Coming out of here, I've got north-south green. Well, north-south green is what? A bar, B bar. So let's go ahead and grab A bar. There I am grabbing A bar. I'll feed that into that AND gate. And then what else? B bar going straight into the AND gate like so. All right. What next? North-south yellow. That's a good one to do. Another 2-input gate over here. So we'll draw that in like so. This would be north-south yellow. Okay, what is this? A bar B. So let's feed in A bar. So here is the A bar once again. Connect to A bar. And then we'll feed in connection to B, feeding in B. So that's north-south yellow. North-south red, of course, is just A. All right, so let's just grab A. There is A, piece of wire, straight piece of wire. Okay, and we're saying that that is really north-south red. Okay. All right, what else do we have? Well, we have wait and we have go. All right, so wait is what? Wait is basically the OR of A bar and B bar. So it's the OR of those. Okay, so we'll just do that, the OR. So here we go with the OR for wait. Here is my OR gate. What do I want to feed into the OR gate? A bar. So I'll grab A bar, feeding in like so. And what else? B bar. B bar feeding into the OR gate like so. And then of course this is what? This is my wait output. All right, so that's the wait output. Let's do go. What is go? Go is AB. All right, so it's just an AND gate for go. 2-input AND gate. and we just have feeding in, we have A, and feeding in, we have B, and that is the go light. All right. Now our special outputs, of course, are AN and BN. We'll look at AN. What is this? This is our exclusive OR function of A and B. It's exclusive OR of A and B. So we'll go ahead and show that by way of our exclusive OR gate. There it is, sitting there. And of course that is AN. And we need to, feed into that exclusive OR A and feed in B. Okay, that is AN. BN, well, this is an AND/OR situation. Okay, we've got an and, so it's a product of sums. So let's just go ahead and show that over here. So here's the first AND gate. First product term is what? A, B bar. So let's get A, B bar. So here is A, grabbing A here, and I want to feed in B bar, so I'll feed in B bar like so. All right, next product term. What is the next product term? Well, we've got the switch. Yes, so I better sort of bring in that switch. So here is the switch. Oh, look, maybe I'll just bring the switch up like this. But that's my switch input feeding in. Okay, what else have I got? B bar. So here is B bar. So B bar is coming down like this, feeding into that gate. And of course it's an AND/OR giving me BN like so. All right, so basically I've now got the logic here. Of course, this is the A, this is A bar, this is B bar, and this is B bar. Okay, so I've just got, at the moment, a wire for A wire for A bar, a wire for B, and a wire for B bar, and where I'm showing the dots, those are the appropriate connections to the logic. All right, so now effectively I'm really building, am I not? I've produced the logic for the state table. Okay? Okay, so I now have the logic for the state table, which basically is the logic in this block over here. What I now need to do basically is connect in the two flip-flops which provide the A and B values, and then we'll think a little bit about this switch over here. Okay, once again I'm showing you the logic that we've now implemented that implements the state table. Okay, I put in these two flip-flops here, and of course really if this is the A flip-flop, Q would represent A, so we might as well just draw that in. Here is Q, which is providing the A, and of course note that you have a Q bar on here, which really is giving me what? Is giving me that A bar. Similarly, if this is the B flip-flop, okay, I can use that Q to provide, of course, B, and then this Q bar over here, of course, is really providing the B bar. Okay, so that's the A flip-flop, that's the B flip-flop there, which is providing, if you like, the present state. Okay, now remember, what are we doing here? We're feeding back the next state information to the D inputs of those flip-flops. So let's go ahead and do that. So we'll come across like so, and we'll connect BN. And then once again, we'll come and connect AN, and we're going to connect AN to the D input of our A flip-flop sitting up here like so. All right, so effectively now we've completed this. We've got our complete state machine. Of course, we've got our clock input to consider. We've got our switch to consider as well. All right, so look, we might as well just quickly, as it were, address maybe the switch consideration over here. How might we want to build this switch? We'll be doing more work with this in the next video, but let's look at that for a second here. The crossing switch, well, it could be a push button switch. Now there are issues and problems, as I say, we'll discuss next time, but if I were going to implement this as a push button, now we might look at the push button switch in this fashion. Here it is, okay. Now if I connect this guy to ground like so, and I connect a resistor up here like so, and I attach that to 5 volts, is that going to work? Is that going to be what we want it to be at this point? Well, let's think about this. If the switch is a normally open switch, then this voltage or logic level here would be what? If it were a normally open switch. Yes, it would be a 1, wouldn't it? And so if I'm not pressing the switch, it would be a 1. That's not what I want. I want a situation where when I press the switch, S would be a 1. I mean, that is consistent then with our state diagram, okay? Remember, when S is a 1, that's what causes me to change states on the next clock edge. So you could do it this way. The only thing is that you would want a normally closed switch. Okay, so really you want a normally closed switch sitting here, so that when you press the button, you open the switch, therefore creating S or causing S to be a 1. So when you push it, you want S to be a 1. That's why I'm saying here you want a normally closed switch. Then of course at that point I can simply connect like so. All right, now if you didn't have that kind of switch and you had a normally open switch, then you just simply have to put an inverter over here to take care of that problem. Okay? Okay, now I'm showing you the actual connection of the clock over here. All right, so we have a Coleman clock that's now applied to both of these flip-flops. Now remember, we only change state when I get the leading edge of this clock. All right, now where you're going to get the clock from, you could use the signal generator in the lab. If you wanted to do this, just make sure that you actually look at the clock waveform before you apply it. You might want to set the clock period to a couple of seconds. Remember, this is a traffic light system. And make sure that the clock is going from 0 to 5 volts. The other thing to mention, I suppose, over here could be in relation to these light outputs here. These in our design are now high acting signals. If we wanted to make them low acting signals, then basically all we need to do here is basically what? Put an inverter here. It's kind of like putting a bubble here, which makes this into what? A NAND. Same with this. If you want this signal to be low acting, just invert it. Put a bubble here. It makes this into a NAND. Same with this guy here. Okay, maybe we want to put an inverter in here, or maybe alternatively we can actually take it from A bar over here. Okay, in this case we want to put an inverter which makes this what? Makes it a NOR gate, and then an inverter here which would make this a NAND gate. Okay? So therefore we could make our light signals, if we so chose, low acting in a very, very easy way. Okay, now going back to this clock issue over here, as I said to you, we could provide that clock from a signal generator and watch our light sequences going through. Alternatively, we might want to have the capability where we could single step the clock. In other words, if I had some kind of push button type of arrangement where I press the button, as I press the button, that creates the leading edge of the clock, which causes me to change states. Okay. If I press the button again, I get another leading edge of the clock, and I'll change states again. Now, in this mode, I could actually manually single step then through the appropriate states. So I could move into a state, and until I press that button again, I will stay in that state. And this is a very good debugging tool, so that you can be in a given state. You're not going to come out of that state until you press the button again. So I think in the next part here, what we'll do is we'll spend a little bit of time talking about how we could generate, as it were, a manual clock, and what some of the issues are in doing that. So look, we're going to take a break at this point, and then when we come back, we'll look at this manual clock situation. Okay?